So, all right, cool. So here, determine whether the following infinite sequences, not series, but sequences for diverse. So just review what we did in the previous lesson. So you have an alternating component, the -1 raised to the n, which does play a role because it's going to go back and forth between -1 and 1. Then up above, you have n plus 1 over n. Now that reduces to 1, right? Because we see that the n plus 1 over n is a rational expression. Remember, when the degrees are the same, the ratio of the leading coefficients will be your limit, right? As n approaches infinity. Or you can say Paul's rule if you want, you get 1 over 1. But the problem is that you still have that alternate component next to it. And it's just going to diverge because you see that alternating component. So you don't really have to say much more than that once you show that alternating component is going to play a role here. So I do know the rational portion is going to converge to 1. That's cool. If you didn't have that -1 raised to the n, then this would converge and it'd be 1, right? Problem it's not. For B, we could do a squeeze theorem. So why did I choose 1 over n squared or -1 over n squared? Because what's the range of cosine? 1, -1. So if you replace the top with 1 and -1, you know you're going to get the highest it can get or the lowest it can get, right? And each of those outer limits, outer expressions, the limits of those, -1 over n squared, 1 over n squared, both converge to 0. So naturally, the middle has to converge to 0 as well. So that's how you can prove it. So these are just more ways to prove your answer right. Then the more recent stuff, right? Okay, look, what was happening here, right? So we see that, oh, it's 2, and then 6, and 12, and 20, and so forth, right? But we're looking at partial sums, by the way. The sequence would be 2, 4, 6, 8. But the partial sum, 2, 2 plus 4 which is 6, 2 plus 4 plus 8, which is 12. Sorry, 2 plus 4 plus 6 is 12, and 2 plus 4 plus 6 plus 8, which is 20. So we see that follows this pattern n times n plus 1. Of course, that's going to diverge, right? If you take the limit of that as n approaches infinity, that's a polynomial expression. Of course, that will diverge. For B, you have -2, 2, -4, 4, and so forth. But the pattern, the terms are -2, 4, -6, 8, and so on. I think I have to check with Ms. York on this one. She's been out sick this week, but I'm pretty sure I put a question mark last year. Do you guys say diverge? Yeah, I'm pretty sure. Yeah, because I don't see how that would converge. I think maybe someone was questioning me on it last year. Can't remember who it was, but anyhow, I would say this would diverge. I mean, obviously, every odd term goes towards negative infinity. Every even term goes towards positive infinity. But ultimately, if you think about, yeah, if you just think about what the partial sums are, um, and then what happens, I don't see how this would ever converge anything. So anyhow, we'll keep moving. For 3, very similar to one of the problems we did in the notes. I think it was one of the last problems we did. So this is broken apart into 2 fractions, and you can just rewrite every pair like, oh, n equals 1, I get this, n equals 2, I get this, n equals 3, I get this, and so forth. So if we just kind of just forget about partial sums, kind of just forget about that, and just say, well, let's say n is like 10, right? And you kind of work all those terms out, you're gonna see a lot of canceling happening. The only things that don't cancel are 1/2, 1/3, -1 over n plus 2, -1 over n plus 3. When you write it all out. And then if you combine the 2 fractions that have n plus 1, n plus 3, n plus 2, n plus 3, combine 1/2 and 1/3, work it out, you should get 5/12 minus that junk. And of course, when n approaches of that junk is going to go towards 0. So you get 5/12, so that will converge. So looks good.
So they asked like find the partial sum formula. Which part this is?
I didn't do that.
Oh.
I didn't do it. I just determined whether this thing. I avoided that because it was been too messy. Because I'd have to first say, okay, well, I mean, it is technically it is this, but I didn't feel like writing all the partial sums because okay, let's find some one, but some of the first 2 terms, some of the first 2 terms, some of the first 4 terms. Then I'm just writing this like a whole bunch of times, which I didn't feel like doing. So I just kind of just figured, you know what, we'll just have this go forever. Like, how will this look going on forever, right? So I know I'm gonna have this, I'm gonna have this, and so I'm gonna have all these terms like put in 1 frame, put in 2 frame, put in 3 frame. So this right here doesn't really represent necessarily a partial sum. This actually is kind of showing what if I just went forever, right? and then recognizing that a whole bunch of things cancel except for the first two and last two terms. That's why. So I didn't really waste my time doing what I did for like here, like for number 2A, I wrote out the partial sums, right? 2, 6, 12, 20. Here I wrote the partial sums to see the pattern. But this we kind of suspect, as we saw from the notes 2 days ago, we expect a bunch of things to cancel. So that's what's happening with part A. For part B, it's a geoseries. Hopefully you can recognize that. There's an alternating nature to it. Actually, not really, because it's 2n. So we got lucky because no one squared is 1 anyway. So the alternate nature is actually neutralized, so we don't have to worry about that. So it's 1, 1/5, 1/25, 1 over 125, and so forth. Once you recognize it's geometric series where the ratio is less, is between a 1 and 1, or the outside of the ratio is less than 1, then cool. You have the formula, just work it and you're done. You're good. Ready?
Why we started just like writing all the values for like when n is 1, n is 2, n is 3. Like why did we stop doing like S1 and then like adding them and then
I was just checking the pattern for the sequence. So I didn't do a partial sum for this one. You're 100% correct. If I did a partial sum, the partial sum would have been 1 with sum 1, sum 2 would have been 6/5, sum 3 would have been whatever these three added to, and so forth. The reason why I got away from that, because I recognize it's a geometric sequence. I recognize that each term is going to follow a geometric pattern. And so all I need to do at that point is just check the ratio. And if the ratio is between A1 and 1, then I know the series will converge. I don't actually have to write the partial sums. So I decided to get away from that because I knew the pattern was geometric. But like I didn't know what to expect with both these patterns. So I felt like I should write the partial sums, see what's happening. And then I recognized, oh yeah, I could express this as a formula, or I could see a pattern with this and recognize that, yeah, these are not going to converge, just going to diverge. So I felt like doing it for that one.
So how do I like recognize when to
If you see geometric, just don't worry about it. But I would say the default, do write out the partial sums unless you see it's geometric. Because that's the one consistent pattern that we've only talked about so far. Everything else has been kind of free for all, as you can tell, right? Because they're all kind of they all kind of have their own beats, right? And they're all kind of weird. But 3B is the only one here so far that we've talked about today that does follow some sort of consistency. So if you see that, if you recognize it, forget about the partial sum stuff then. Just go straight to the form that you know. That's my advice for that one. Mm-hmm. Laura? Yeah, but the things that I don't feel like adding all those fractions up because I already know what's happening. So I'm not going to waste my time doing it. But most things you should. And that's what I'm saying. The default you should, unless you see the geometric pattern. So that's just more of a recognition. I think that, and I have to kind of, I mean, I actually I kind of wish Ms. York was here so I could ask you these questions because you guys are asking fantastic questions. But and we did this a year ago when we retooled this unit. But my thinking, her intention was she wanted you to kind of see what a lot of random stuff looks like. And among all that randomness, can you identify the one pattern that's not random, right? And that's the geometric series. So yes, you should, as a default, write these out. But ultimately, if you can recognize that pattern geometric, just bypass all that junk and just go straight to getting the answer. And I think that's what she wants to be able to see, that consistency among all the noise. There's a lot of noise here for sure. And I think that was the intention of designing notes in this way. But I have to ask her because it's been a year since we retooled this. For 4, looks like these are well, not all of them, but most of them are geometric patterns, right? Definitely A is, but the ratio is -5/4, so forget about it. Definitely B, and the B is a funky one, right? Because if you use your properties of exponents, you have to get a little creative. So this requires a little algebraic creativity. 3 to the n-1 is the same thing as 3 to the n times 3 to the -1. So notice that e to the n, 3 to the n both have n as their exponents. So you can consolidate that as e over 3 raised to the n. 3 is just pushed off to the side because that's 1 over 1/3. So that just gets pushed off to the side. So your first term, if n is 1, would be e. There you go. The pattern, the ratio is e over 3. Now, what is e roughly as a number? Euler's number is 2.7. 2.7 is less than 3. So overall, the ratio is definitely less than 1. This would be, and don't worry if if you didn't have a calculator for this one, I think you'd still be okay. If I asked you to leave the answer in terms of B, you'd be fine. It'd be okay. This actually might could lend itself well to a multiple choice question, perhaps. I could say, here's the sigma notation expression, and which of the following expressions would it converge to? Or I could say it doesn't converge. But that could be a good multiple choice question. And the question could be, does if it converges, what does it converge to? And one of the choices could be does not converge, or just a bunch of other expressions. So kind of like that one. Kind of requires some number sense. Before I get to E, if you look at D, again, you could rewrite that in that manner. And when you rewrite this, try to make sure you pick bases that have the same exponents. In this case, it's rewritten in such a way you have -6 raised to -n, 8 raised to -n. You can flip them, right? Flip them. So you have 8 to the n up tops, -6 to the n on the bottom. That comes -4/3. That ratio is definitely less than -1. Forget about it, diverges. So that's what we're really trying to get at. Is like, can you just recognize a geometric pattern? And as I mentioned in the notes for this topic, like there are 10 different tests of convergence. Geometric's one of them. It's one that you're most comfortable with because you've seen it so many times now. I might teach one of the other 9 next week. I got to, again, talk to Ms. York because we do have some time to still cover stuff. And actually, interestingly, we're going to cover more material than I did last year. Because next week, just to be honest, like of this current unit, I'm actually out of material. So, but there might be some more material I could still throw in there. You guys probably were like, no, Mr. Don't teach any more material. We could be all done. I don't know yet. Let me, but I will say this tomorrow, I am going to pump the brakes. I'm going to pump the brakes, not teach new material tomorrow because a lot of you guys have APs next week. And I think what would be good would be to kind of just sort of check in and make sure, hey, do you understand the last 3 topics we've talked about? Do you guys feel comfortable with that? So what I'll wind up doing tomorrow is giving you guys the test I gave last year. Just kind of check to see how you're feeling about the stuff. Also tomorrow, I'm going to start preparing final exam materials for you guys. We are, believe it or not, about 3.5 weeks away from finals. Finals probably don't mean much for the juniors because you guys probably already did all your finals this week and last week. But for sophomores, that might mean something because you have a lot of other finals. For the juniors, am I the only final you guys have, or maybe 1 or 2 finals? Yeah, so that's it, right? So I'm gonna start preparing some stuff next week. Sorry, tomorrow, so you guys can start getting a head start if you want. I assume you probably won't touch till after APs. That's totally fine. But I have a thought of what I want to do for final exams. Like I think I'm probably gonna do about 12-ish questions, maybe 2 from this topic, this unit, 2 from the previous unit, and make it more calculus heavy. Definitely a problem on linear motion, maybe an exponential derivative word problem, some of the chain rule, some limit stuff. Maybe like one of those questions where you have like I give you a bunch of like information, you have to draw a diagram from it. I'll have it all kind of more fully formed by tomorrow. But I have a thought of what I want to do. So I want to make sure you guys get a head start tech because next week I'm probably going to cover some new material. I haven't decided yet what that will be. The week after, we'll start prepping for our test for this unit. And then we have 1 more week of review for finals, and then that's it. We're done. So, Teddy, go ahead. Yeah, okay. What was the question? We will, yeah, May 14th. And I'll have to be flexible about because I know there's going to be some conflicts with APs too. But yeah, anyhow, we do have a bit of a luxury because I could still throw in some new content in this unit. For part C, that's a funky one, right? So what we want to do is list, it's not obvious, but this is actually following a geometric pattern. It does. I mean, so if you just plug in 0, plug in 1, plug in 2, plug in 3, you start noticing, oh, there is a common ratio. The common ratio happens to be -√2. Well, √2 is 1.4 something. That's less than 2. So this will converge. I like C a lot because it's so cryptic that this kind of forces you to work them out. And actually, it also forces you to do some trig, right? You got to know your unit circle. So unless I gave you a calculator to do this problem. But even if I gave you a calculator, I still think it's better to kind of work it out in this fashion because you're gonna have a bunch of decimals, right? If you do in the calculator, it's gonna be hard to tell. It's a little more obvious and it's obviously precise because you see for yourself, oh yeah, it is negative root 2/2, the common ratio. And then you can work it out and get the answer. So yeah, anyhow. So that covers the homework. Any other questions on the homework at all? Hope you guys feel a little better about it. And again, to answer the question, like, how do you know when you do partial sums or not? Do the partial sum, do calculate, unless you see it's geometric. If you see it's geometric, just go straight to that formula, A1 or 1 minus R. Just go straight to it and give me the answer. Okay. Let's keep moving. So the notes, let me pass it out. If you're doing the notes electronically, it's going to be in Schoology. It's going to be called Introduction to Power Series. Okay. And let me hand this out.
And again, it'd be nice to look copies. Good.
Okay. Let's talk about the notes. All right. And again, the plan is I think we can get through all this today. And again, tomorrow will be just a chance to kind of sort of just pump the brakes. I'll print like the test from last year, have you work on it. If you're feeling a bit of a crunch with APs, I can be somewhat flexible. And if you want to do more review for another class, that's okay too. But we should kind of sort of do a nice little check-in, like, hey, are you understanding what we've done for the last 3 classes? So anyway, so what is the power series? That's what we'll talk about. When does geometric power series converge or diverge? What is interval of convergence? That is a big term, a big thing that is done often in AP Calc species, interval of convergence. So we'll talk about that. How do we find for geometric power series? So again, we're going to talk about what a power series in a moment. How can we express a geometric power series as a function and vice versa? So all these questions, right, we're going to answer. So first of all, let's introduce what a power series is, right? So as you can imagine, a power is when you raise something to an exponent, right? So like 1, 1/4, 1/16, 1/64, 2/5, 4/15, 8/5, -6 over 135, or 1, 3, 9, 27. You start noticing that that's like 2 squared, 4 squared, 8 squared. Like you notice, or 2 squared, 2 to the 4, 2 to the 6. Perhaps there's a lot of ways you can see it, right? Or here, that's like looks like you're squaring, like that's 1, that's 3, then 3 squared, 3 cubed, perhaps 2 to the 1, 2 squared, 2 cubed, 2, 4. So we're noticing some sort of power pattern, right? That's what we're noticing here. Also, we notice that these are geometric, right? So what are the ratios of each of these? What would you say for the first one? How about the second one? Good. How about the third one? Yeah, easy, right? And in terms of their sums, because now we know about the ratio, obviously this will converge, and diverge. And the sum for the first two would be 1 over 1 minus 1/4, which if you clean it up should be 4/3. And the sum here would be 2/5 over 1 minus -2/3, which should be 6 over 25 if you work it out. Sorry, that 2 looks really ugly. Do better. Oh, that could work. Hold on. We'll do a little better. Cool. Okay, all's good there? All right. So next up, next to the infinite series. Okay, so obviously, what's the ratio for this one? X, yeah. That's pretty easy, right? Ratio's X. Okay. And still a geoseries. Now, using this expression, write the infinite series you get when you substitute the following values of X. Well, obviously that's 1 plus 3/4 plus 9/16 plus dot 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 plus 3/4 raised to the n power. Okay. Go and do the same thing for next two. So you're replacing X with the value you see right next to it. And then you're writing some sort of expression afterwards. So you should get 2 plus 4 plus 2 to the n power, right? Where you should get actually -2/5 plus 4/25. And that's -2/5 raised to the n power. Okay. Which really can be thought of like this. If you so desire to pull out the -1 to the n, you can do that. So look back at the first three infinite geometric series from above. Can any of them come from the infinite series 1 plus x? And if so, what would the value of x be for each? So if we look back at, say, this one right here, can I express it like this? This is the whole point we're trying to do. So this is called a power series system.
Right, because you're taking X rate as part, and technically, one is X some power. X one power to one. Yes, X0, X1, X2, X3, X4. That's called a power series system.
Because you have a bunch of powers at the same base, right? And it's a series, you're adding them all up, right? That's called a power series. And what we're trying to do is we're trying to think of the geometric series as this expression, 1 plus x plus x squared plus x cubed. Because ultimately you do a lot of these types of series in AP Calculus BC. So the answer is yes, we can. We could think of each of the series up above, like 1, 3, 9, 27, and so forth. Somehow, some way we can express it in this manner. We can eventually do that. So let's move on to example 1, next page. And looking back at our answers above, give one other value of x that when plugged into this will produce a convergent infinite geometric series or a divergent infinite geometric series. And this is open-ended, but it's not like just one answer. Like so many answers could work. So what would be an example that x could equal to make 1 plus x squared plus x cubed plus x4 plus dot 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 plus xn plus dot 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 an infinite geometric series that converges? 1/2, sure. Yeah, 1/2 could work. 100%. Because you have 1/2, 1/4, 1/8, 1/16, and so forth, right? So that's an example, right? Just know there are infinite possibilities. What about if I want to make it divergent? 2, 3, 4, 5, whatever, right? Again, there are infinite possibilities, right? So now a deeper look at power series. So this type of series that contains variable x generates different infinite series depending on what you plug in for x. This is an example of a power series. power series is an infinite series that contains variable x but has a certain form, one for which each value of x, one for each. Yeah, okay, fine. That will be defined more formally next year. A power series generates specific infinite series. This series is also geometric, so it is geometric in nature, obviously, because there is a common ratio, and we call this series a geometric power series. And the common ratio, of course, is x. You will see some that are not necessarily geometric, and some will involve like there's like Taylor series, Maclaurin series, like all these weird names. Some will involve like factorials, things like that. But this is actually, I think, one of the more straightforward ones. So, and in order for an infinite geometric series to converge, absolute of R must be less than 1. We know this. So if as x will produce convergent geometric series. So again, stuff that we already know, right? Nothing too new. And you can write it a few ways. You could say, so express an inequality in interval notation, you could write like this. Or you could write like this. Or you could write like this. Or if we want to really kind of get really nerdy with the math, has anyone ever seen this symbol before? It's like a rounded E. So you know what that's called? As far as set notation, it's called element. So you're saying X is an element um, between -1 and 1, non-inclusive. So that's what you're saying. Or a number between -1 to 1 is an element of X, or X is in that set. So um, what we just generated is called an interval of convergence. We know this is an interval of numbers, right?
And do these the numbers in this interval cause convergence for the sum?
Yeah.
Hence, that's what's called.
So don't make it seem like it's so complicated. Like interval converge, what does it mean? Like it just means, hey, what numbers makes it converge? That's all it means. So that's all that's happening. So every power series will have interval convergence. This interval can be a small, does only contain one value of x, or as large, containing all real numbers. So again, these are things we'll talk about next year. So let's move on to example 2. So we want to know specifically what will make this converge, what will make this diverge, or just some examples, and then how do we actually truly find it? So again, this will have infinite possibilities. So just give me a value of x that would make this converge. Was that? Sure, 1/8 works. Yeah, I like that. Works for me. I wouldn't say 1/2 because then then you have like 1, 1, 1, 1, 1, 1, 1, 1, 1, like that. Your ratio would be 1 in this case, right? And it can't include 1. So don't do 1/2, which kind of helps us figure out part C, actually, if you think about it. But 1/8 is a possibility. That works. Sure. That's fine. And obviously that makes it diverge. Yeah, sure. 1. 1 would make it diverge because you have 1, 2, 4, 8, 16. Yeah, 100%. So is this a geometric power series? Of course. And what's our ratio? What do we multiply? 2x, right? So what this means is that the absolute value of 2x has to be less than 1, or this is true. Probably easier to solve the one on the right. And that's it. That's your interval of convergence. If you write it in interval notation, and by the way, IOC, just like how we have like POI and all these other abbreviations, this stands for not International Olympic Committee, interval of convergence. Or you could write like this in interval notation like this. That's fine as well. It also works. So that should be pretty straightforward. Just figure out R is in terms of X. and just throw into this inequality and solve it, right? It's not that hard. Okay, any questions so far? We're good. All right, let's keep going. Okay, example 3. Ooh, this looks a little crazy. All right. So again, obviously this is the S. This is R. We got to figure out the IOC. I'm going to do part B and C on your own or in your table groups, but give me examples of values of X that would make this converge or values of X that make this diverge. So give me an example that would make this, because remember, you want the ratio to be between -1 and 1. So what value of X would make this okay to converge? Do you think? -3 is good, or -4. We'll go -3 because you get 2/3, right? So now you're multiplied by 2/3. And what would make it converge? Like X equals 1 would not be okay, right? It would keep converging. Sorry, it would keep growing. So it would diverge. Okay, figure out what R is in terms of X, and then solve for the interval of convergence. Okay, what's your R value? And what do you guys get for interval of convergence? Perfect, good. That works for me. Yep. And it's kind of nice to kind of, by inspection, figure out question, Lucas. Okay, let's work out. You definitely made a careless mistake, but let's figure out where it is. Okay, you're good. So careless mistake happens. Okay. So the conclusion: a geo-power series, the interval convergence can be found by putting in the common ratio into the inequality net 1 to 1, and just solving it. That's all. So very, very basic, right? Okay. Okay, example 4. Okay, so we're gonna do something different this time. Actually, let's go back over here. The other thing we want to do too, which I kind of need to mention, we also want to find the center of the IOC. And what would the center of the IOC be? Yep, -5. That actually will matter tremendously in AP Calc BC when you do the series unit. Because you'll be given a series like, here's a series centered at this X value and a bunch of stuff you got to do with it. I mean, it's pretty obvious it's -5 because, obviously it's 3 away from both endpoints. So again, it's not that hard. That will play a role much later next year in AP Calc BC, where you'll be told that you have to write a series or come up with a series centered at this value of X, like at X equals whatever. Let's develop a series, and you'll be doing some sort of calculus stuff with maybe a derivative or integral, whatever you got to do with it. It's just a terminology. I mean, it's not a hard thing to find. Just find the middle of those 2 endpoints, right? That's all you're doing. I'm just exposing you to that terminology and just telling you that's something you will hear often next year. So, Kingston, go ahead.
Will we ever have our series that's going?
Yes, you will.
Okay, and then
yeah. So those some of the comments are called Taylor or Maclaurin series, and they're kind of these very funky series that involve like factorials and derivatives and things like that. But I'm not going to talk about that with you guys because that's beyond the scope of what we do.
So like just for this class,
Keep it kind of like more basic, foundational, just to kind of get you understand the idea of this. That's all. That's really the intention of this lesson. But as you can tell, it's pretty manageable from a mathematical standpoint. So, okay. So here we're going to find interval of convergence again, write the final answer interval notation, and let's find the center as well, right? So we should identify what R is first. Always identify your R value in terms of X. So what's R gonna be for part A? Negative 3X. Okay, what's R gonna be for this one? Yep, negative 1/2. Or you can say, yeah, negative 1/2 times X minus 3. You can write like that. So now find your IOC for each. And we'll just throw this in. Give me the center for each as well. By the way, if you ever multiply by a negative, what does that do to the direction of inequalities? Flips. Whenever you multiply by flips, right? Do you guys know why? Yeah, you want to guarantee the same answer. Like if you have like negative 2x, it's less than 6. X is greater than negative 3. Because you have to guarantee that if you did a little switcheroo, that you still get the same thing. You have to still guarantee the same answer if you decide to move the terms from one side to the other side. So that's the reason why we flip when you divide by or multiply or divide by a negative. Okay, first one should be pretty obvious. What do you guys get? Center around 0. Okay. And what do you guys think about this one? For part B. 1 to 5 and center around 3. Yep. And it's not a coincidence that you have X minus 3. So ultimately, you'll have to like devise your own series when you're given some information about it. If you're told, hey, I need a geometric series that's centered around 3, you would do something like that. So okay. Let's keep on moving. We're okay with these two? We're good? Yay, nay. Good. Okay, cool. Let's keep moving. Okay. Representations of functions as power series. Okay. So let's take a look at how we can think of this as a function in a way. You'll see that in a moment. So yeah, it is useful to represent certain types of functions as a power series. That's just a useful thing as you'll especially next year. But to understand how power series can represent a function, we'll go back and consider the most basic power series, as we just saw, 1, x, x squared, x cubed, and so forth, right? That's just sigma notation x dan. And we know this converges when x is strictly between a 1 and 1, non-inclusive, right? We also know how to find the sum, right? We know this. S equals whatever what? Yeah, A1 or 1 minus R. Or we'll just call it A straight up. A is the first term. But in this case, A is going to be 1, and the R is going to be X. So if you think about it, can I express the sum as some sort of function? So what's my A value? 1. What's my R? So if I replace A with 1 and R with X, what do I get? And what kind of function is that? It's a rational function. So a rational function can be used to express a power series. So that's what we just did. We just created a relationship here. So a rational function can be used to describe power series. Okay. And of course, X has to be between what and what for this to make sense. Yeah, -1 and 1. Otherwise, then the sum can't be found, obviously. So now take a close look at the statement above. You just create a relation between a function and a series. That's what you've done. And that's kind of a big deal in calculus, AP Calculus BC, to be able to do that. So the sigma notation, n equals 0 to infinity, fine. You have 1 plus x, whatever, right? And remember, we always want to start with n equals 0 because you want x is 0 as your first term, right? X is 0 as your first term is 1. And it's represented by the function 1 over 1 minus x, where x is between -1 and 1. And we know how this looks graphically. This has an asymptote at x equals 1, has a horizontal asymptote at y equals 0. So from this relationship, we can create other relationships between functions like 1 over 1 minus x, or other power series similar to the one above. But we're only going to focus on this particular power series, 1, x, x squared, x cubed, x forward, and so forth. There's a whole bunch of the power series to see, and you will have to somehow connect it to a function. And what's going to happen is that you're going to be doing some sort of calculus stuff, like derivatives, antiderivatives. But it helps if you convert this. This helps it. And this conversion is easy to see because you know it's geometric. So I just replace a with 1 and r with x. That's easy to see. Okay, so you have a question? Correct, yeah. You want this to converge, yes. Yep. All right, so this case, given that 1 over 1 minus x equals this power series, right? On the interval from -1 to 1, find a power series that represents each of the following. Okay, so here's where you gotta get a little creative now. And I think this was the intention of Ms. York's notes, is to help you get creative with re-expressing these in such a way so it looks something like this. You have to get a little creative with the algebra here. So you're asked to find a power series that represents each of the following functions. Okay, so a power series has to involve, like, 1 with x raised to some power and so forth, right? So this part, you're probably not sure how to approach this problem, so just kind of follow my lead here. And hopefully you kind of see what I'm doing. So you want to write in this form, 1 over 1 minus something. You want to express this like this. What would I put in place of this question mark? So it's the same thing as this. That's correct. That's what you want to do. Your goal is to rewrite whatever you're given as 1 over 1 minus something. That is your goal. So that's the goal here. The goal is to rewrite the expression as 1 over 1 minus something. Find that something. So of course it's -x. Okay. Now, if you think about it, that's A. That's R. So now when you're asked to write a power series, what's the power series? 1. What's my second term? If my ratio is -x. A is 1 and my ratio is -x. -x. What's the next term? What's the next term? Plus dot, dot, dot. It'll be -1 raised to the n power. And then, of course, x to the n.
Do you recommend breaking it up or does it matter? Like, can we just do -x for that?
It's up to you. Yeah, you could do -x, yeah, that's fine. It's just a good idea to do -1 to n because you'll be talking about alternating series as well. And so it's just it's good to be able to see that. I mean, if you wrote -x to n, you're fine. It's not a problem. But if you do that, make sure you put in parentheses. Just be mindful about that. Because if you wrote like this, then all terms are negative, right? So I think It's just to somewhat be more intentional, putting the -1 in parentheses. What is the IOC here? Still going to be between what to what? Yeah, still it's between -1 and 1, because if you have -1 is less than -x is less than 1, and you flip things, it's still going to be the same thing. So, okay, let's keep moving. Okay, so still the same instructions, right? We have to do more rewrites. So that's A. Actually, don't just have to do a rewrite. It's really more a matter of understanding what R is. So again, it's 1 over 1 minus blank. So what do you put in place of the blank here? So your A is 1, and your R is 2x. Or one thing that could help, actually, what if you come with an arbitrary letter, like let's say called well, actually we'll just call it R. What the heck? Right? And that's what it is, right? If you think about it, we'll come back to part B in a moment. But if you think about C, right? The denominator is x, but you really want it to take the form of 1 minus R. What would R have to be to make that true? If you move things around, what do you get? Yeah, you get 1 minus x, correct. Or -1 times x minus 1. Uh, before we do part D, let's actually finish off part B and part C. So let's write the power series of this down. The first term is 1. What's the next term? Next term? 4x squared, right? Next term? So in general, it's 2x to the n power, or 2 to the n times x to the n, if you want to write it like that. Interval convergence should be pretty obvious. And the center is 0. Okay, let's go part C. However, this is a power series. 1. And now that my R is 1 minus x, or -1 times x minus 1, I could think of it like this. That's kind of a cleaner way of writing it. This is going to be -1 raised to the n power times x minus 1 raised to the n power. Yeah. That's kind of a cleaner way of thinking about it. It's kind of the habit of like writing it in a more consistent manner. Yes, if you solve for R, it's 1 minus x, but personally, I think I would much prefer to write it this way, because now you see it's centered at 1. And interval of convergence is from what to what? 0 to 2. Yep. Your IOC is from 0 to 2. And your center is at 1. So what I'm giving you guys is kind of like the foundations or the building blocks that you'll need for the series stuff in AP Calculus BC. Just to kind of like get in a habit of writing these things like this. Again, you could have been if you did 1 plus 1 minus x plus 1 minus x squared plus if you did I'll just write on the board. If you wrote like this, 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed. There's nothing wrong with that. You're not wrong. That would be totally a-okay. And if you wrote this generally as 1 minus x raised to the n power, that's fine. You could. It's just preferable to write this way so you can see that alternating. And you see that x minus some number. You're going to start noticing this is always be the center of the interval of convergence. It's just a habit that we want to establish. But you're not wrong if you wrote like that way in purple on the board. So, okay, questions so far? We're good. Okay. You guys are easy compared to my G period. I'll be a gazillion questions, and I got tell a couple of them to shut up. Anyway, you can probably tell who. Part D. Your part D is going to be funky a little bit. I'm going to pull out the X and think of like this. So I got a little creative here. I deliberately wrote this 1 minus R. Right? Same thing, right? But both X. Who cares? X times is what you do after this whole expression, right? It doesn't matter. Right? So you want to be fluid with fraction. Of course, 1 plus X is the same thing as 1 minus negative X. So if I think about it, I could just really just focus on this. What's my A for that? And my R, of course, is negative X. So if I just focus on this, I'm going to have 1 minus X plus X squared minus X cubed plus dot, dot, dot. But really, what's happening, don't forget about this little X here. It's still there. Really, it's supposed to be this. X times that. That's what it's really supposed to be. Nope. First one won't be 1. Correct. It will be X. So, and then plus, that's negative 1 to the n, X to the n. So after I distribute, and around space here, I get X minus X squared plus X cubed minus X4 plus dot, dot, dot. And of course, the interval convergence is still between negative 1 to 1. Center at 0. So it's very similar to what we did in part A. Just to have an extra X. That's all. Yep.
We like solve an equation, for example, like
Mhm.
x divided by 1 minus x equal to 1 over 1 x. Can we solve?
Yeah, exactly. 100%. Right. Yeah. So we could do something similar for example 6. So find the power series that represents a function for the following. Find interval convergence for the power series. So, right. So exactly what Lucas just said for example 6. Think of this as 1 over 1 minus R. So 2 plus X what's R going to equal?
Negative X over 2.
Not over 2. Negative X minus 1. You were dividing, right? Guess subtract 2. Or you're giving R like that. -1 times x plus 1. So if I write the power series will be this: 1 minus x plus 1, because your a is still 1, obviously, plus x plus 1 squared minus x plus 1 cubed plus dot 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 plus -1 raised to the n power x plus 1 raised to the n power. And your IOC would be from -2 to 0. Sorry, -2. Well, let's solve this really fast. What's your IOC here? No, -2 to 0. I got it. Yeah, -2 to 0. We're good. And it's centered at -1. There's actually another way this could be expressed. I'll get to that tomorrow. I don't want to do that today. And I'll hold off on example 7. I don't want to rush it because Bell's going to ring in less than a minute. So homework, I'll hand out to you guys. You guys still do your homework. Also, going into the power series.
It was like
They go to Marin, they break up. Yeah, I know they break up and then yeah. Yeah, you guys get some pretty strong, and now you get some. Yeah. I have your test, so. What do I do? Never mind. Never mind. I have every all of them. Yeah, go.